very much. This is work done by a lot of people over a couple of decades. So according to what lots of people say, there's such a thing as magnetohydrodynamic turbulence, and it would fill up all space, and it would be homogeneous and be characterized by a spectrum, and people argue about the spectrum. And one manifestation of that was something called Taylor relaxation. This is not the G.I. Taylor that you hydrodynamic people are familiar with. This is Brian Taylor, also in England, who was trying to explain how a fusion device worked, but it was also a turbulence argument. So the idea was that the plasma would fill up a volume and the system would relax to a lowest magnetic energy state subject to conserving magnetic helicity, which is the linkage of magnetic flux tubes with each other. And you had to impose boundary conditions in order to quantize the modes associated with this. The detailed argument required an integration by parts, and you had to have a boundary to work with there. And then the argument was that you get a slow evolution of this turbulence and it would eventually settle down to a relaxed state, and you didn't have to follow the detailed dynamics because it just wanted to go to the lowest energy state. And this lowest energy state would be the longest wavelength mode that was consistent with the boundary conditions and that conserved helicity, and it was a kind of inverse cascade. So I constructed a lab experiment to study Taylor relaxation because these devices actually work. People have done experiments. They made something called a Sfermac that was based on Taylor relaxation, and I wanted to see what actually happened, what the dynamics were. So to do this, you have to inject magnetic helicity and magnetic energy because those are the players in the play, and I wanted to look for the predicted turbulence. And the plasma parameters, for those of you who are familiar with plasmas, were that it was a fairly dense plasma. It was 10 to the 22 per cubic meter, fairly cold, about 2 electron volts. We're working with big currents, 100 kiloamps, and magnetic fields were a few kilogauss, and the whole experiment lasted about 30 microseconds. And it was a human dimension. It was like centimeters size. You don't have to use great imagination to see it. It's the size of things you're familiar with. So the experiment didn't see the expected MHD turbulence at all. We weren't seeing this Taylor relaxation. Instead, we saw that there were unbalanced forces that accelerated the plasma and formed a very collimated jet. So it wasn't homogeneous, it was very specifically localized, and it was very dynamic and far from equilibrium. And over the years, we realized there was a sequence of very distinct phenomena. We've been studying these and sort of following them. And we saw 2 different types of MHD instabilities, and then they would lead to a non-MHD phenomena and instabilities. So here's the experiment. It's a human size, and everything starts, oops, wrong button. Everything starts with these electrodes here. It's about 50 centimeters in diameter. So initially there's an empty volume, and essentially we're injecting magnetic energy and mass and magnetic flux and magnetic helicity into this empty volume, because those are all the ingredients for this recipe. And the initial geometry looks like this. We have a coil, or a current loop, shown here, that's making a dipole magnetic field. There's symmetry about the vertical axis, and there's a mass source down there. And here's a picture of what that dipole field looks like. It lights up with plasma that's showing those magnetic field lines, and the diameter there is about 50 centimeters. So we go back to the sketch. So the current loop is producing that colloidal magnetic field or dipole field. And then we add a current source. It's a capacitor bank down here that connects the inner electrode to the outer electrodes. The 2 electrodes are insulated from each other. So we're essentially applying a voltage across here, and we're driving a current, an electric current, from the inner electrode to the outer electrode. You can think of the poloidal field line, the blue line, as being like a wire that's carrying this green electric current. And that current makes its own magnetic field from Ampere's law, shown by these red circles. That's a toroidal magnetic field that's produced by this current, shown by the green line. And we keep on doing that. So there's a continuous injection of toroidal field by that current source. And so the system is going to change, and the current is the same. So we have more and more of these red circles. And so we're doing helicity injection, because if you remember the pictures of helicity injection, it was linked magnetic flux tubes with each other. So we have the blue magnetic field line that's linked by the red field lines. And we're having more and more red circles there, so we're injecting more and more helicity. And it's getting longer. And there are MHD forces that are pushing this around. I could talk a long time on that, but not enough time. Here, I'll just say a little bit about them. And there'll be a voltage appearing across the electrodes, because these red circles are also can be thought of as magnetic flux, and we're injecting magnetic flux. And Faraday said you have to have voltage associated with the change of flux. So there's a voltage between the inner electrode and the outer electrode. That's the rate at which we're injecting these red circles that have to do with the thing getting longer. We're also injecting energy, because there's energy associated with the red circles, with the magnetic field, and that's characterized by the Poynting flux, and that has to do basically with the voltage or the radioelectric field multiplied by the magnetic field associated with the red circles. But we also have to inject mass, because according to ideal MHD, the plasmas, or the magnetic field line, is frozen to the plasma, or the plasma is frozen to the magnetic field line, and we're injecting those red circles, so that's flux going in, and so there has to be mass frozen to that. So we go back to our mass source. We have to have a mass source there, and the orange there is the plasma that's frozen to the red field lines that's getting injected also. So we have dense plasma there, and there are forces. Here's a picture of our experiment having the same diameter. So there are magnetic forces that are tending to collimate this, because we have 100 kiloamps going up, and that's a big current. There's a pinch force that's pushing in radially, but there's also those red field lines there indicate there's a magnetic pressure, a B squared, and a magnetic pressure is pushing up. It's like we're inflating a balloon, and so it's going up. So these two kinds of magnetic forces. One is tending to collimate it, and the other is trying to push it up, and they're both happening. And so that's the jet. So what we've seen in the last few years is there's a distinct sequence of instabilities that are, we start with a macro scale. There's an MHD instability that's called a kink instability, which is kind of the great granddaddy of MHD instabilities. And that corresponds to the plasma wrapping itself into a coil. So the jet hums along for about 25 or 30 microseconds, and then it becomes kink unstable. There's a threshold for that, and it passes that threshold, and then boom, it goes kink unstable. And the kink grows for about 4 microseconds, and then the kink sets up the conditions for Rayleigh-Taylor instability. The Rayleigh-Taylor instability takes place in about a 1 microsecond time scale. And then the Rayleigh-Taylor instability basically pushes the plasma into a situation where it violates the rules of MHD, and kinetic instabilities develop. And this all happens in 1 microsecond. And we see a whole bunch of things: magnetic reconnection, extreme ultraviolet light emission, X-ray emission, and Whistler wave emission during that 1 microsecond. So the observations are there's no equilibrium, there's no turbulence. We can follow all these things that are going on. And instead, there's a sequence of dynamic phenomena, each having different physics. The first part is described by MHD, the later part it doesn't. And MHD basically contains the seeds of its own destruction or failure, because the Rayleigh-Taylor instability, as I'll show you, pushes the plasma into a regime where MHD fails. And each element of the sequence provides the environment for the next. And there are sharp interfaces associated with this conference. And there's essentially a cascade from this larger, slower MHD scale to a smaller, faster non-MHD scale. So let me give you a one-slide education on MHD. MHD involves electric currents, forces, pressure, magnetic helicity, confinement, twist. An ideal MHD assumes the plasma is a perfect electrical conductor. And that means that it can carry an infinite electric current with no voltage drop and no electric field in the plasma frame. And equivalently, it conserves magnetic flux, because the magnetic flux is frozen into the plasma. Because if it weren't, then you'd see a changing flux, which Faraday would say there'd be an electric field, but you can't have that if it's a perfect conductor. Also, big complicated theories show that the fastest growing MHD instabilities are incompressible. Another feature of MHD is it has no intrinsic scale. It's like hydrodynamics. So the same equations apply for laboratory experiments, for the solar corona, and for astrophysical situations. You can put your equations in dimensionless form, and it'll describe all of those things. So now let me mention a couple of physics issues that are relevant here. A complex structure has more inductance, electrical inductance, than a simple one. An inductor has energy 1/2 Li squared, and if you write this in terms of flux, you can show them that this 1/2 Li squared is equivalent to writing it as the flux squared divided by the inductance. And so if it's a flux conserver, then you can lower the magnetic energy by increasing the inductance. So basically, MHD is always telling you the plasma is trying to increase its inductance, because then it can lower its energy. If you take a wire and wrap it into a coil, it's got higher inductance. So the plasma is always trying to do things like winding itself into a coil. And then MHD can fail if the length scale gets really tiny. There's something called the ion skin depth, and there's some other small scales, like the iron Larmor radius. But if you go to that tiny scale, then MHD doesn't work anymore, and then other terms have to be taken into account. Like the inertia of electrons, or something called the Hall term. Another way it can fail that's kind of closely related is if the current density gets to be too high, because according to ideal MHD, you can push infinite current through a plasma, but clearly if you try putting infinite amount of current through something, it's not going to not be happy. And typically this gives trouble when the velocity of the electrons carrying that current exceeds some characteristic wave velocity in the plasma. And plasma is very rich in waves, so there are all sorts of possibilities for that. There's an ion acoustic wave, there's the electron thermal velocity, there's the alpha velocity. So what we see is we see the jet, it goes happily on its way, and then it spawns a kink instability, and then the kink instability spawns a Rayleigh-Taylor instability, and then the Rayleigh-Taylor instability spawns a kinetic instability. And so this sequence connects the MHD scale to the non-MHD scale. And the Rayleigh-Taylor essentially causes the transition to non-MHD kinetic physics. We can also see it going directly from kink to kinetic. And the kinetic instability is associated with the choking of the current channel, and this destroys the concept that the plasma is a perfect conductor, because you're trying, if this were an electric current and I choked its diameter to micron and there's a current going through here, then the current density would become infinite, and at some point things would get unhappy, and that's what's going on in our experiment. So the electrons have to go too fast when you choke it down, and MHD falls apart. So then you have a resistance in the circuit. It's like a bottleneck choking traffic. Anybody driven around California has probably experienced bottlenecks. So here's a quick summary of the sequence. It starts with what we call spider legs, which I already showed you. The inner parts of the spider legs attract each other because of MHD forces, and the whole thing goes up also because of MHD forces. And then on the right, you can see kink instability that develops a corkscrew shape. And this whole sequence takes about 20, 30 microseconds. And here's a movie that shows that. You can see it kinking at the end. I'll show it a second time in case you missed it the first time. Okay, so there's an enormous acceleration associated with the kink. When you put in the numbers, it becomes something like 10 to the 11 meters per second squared in this experiment, because it's happening on a microsecond time scale, and you're basically squaring micro to get 10 to the minus 12. So there's a huge acceleration associated with the kink, because the kink's an exponentially growing instability, and when it's developing this corkscrew, if you're sitting on the jet, you'd be moving sideways with a huge acceleration. So we saw a really Taylor instability. Let's follow this. Oops, wrong button. Okay, so 20 microseconds, 21, 22, 23, 24, 25. So what we're seeing on the top row is the kink developing, and this is the kink wavelength. But then down here, you see some little ripples developing on a faster time scale in about 1 microsecond. And those little ripples are the really Taylor instability, because there's a huge acceleration going up, upwards there, and that means there's a huge gravity pointing in the direction opposite this little arrow here, and that's what gives the really Taylor instability. And we know the periodicity of it just from the picture, and we can measure the growth rate of it, and it's basically scaling like the growth rate is scaling like the square root of kg. We know what g is also, because we can measure the acceleration of this thing. And here's another picture. Now the jet's going from left to right, and you can see the really Taylor ripples on top of the kink. So the feature of the really Taylor ripples is they're making the jet narrower in certain places. They're choking the jet, just like I said I was choking the pen down. And we're putting 100 kiloamps or so through this. So that 100 kiloamps has got to go through a smaller cross-section area, so the electrons have got to go faster. There. So we see a bunch of things happening at that point. These are extreme ultraviolet photos and visible light. The red is extreme ultraviolet, and the bluish is visible light. And in this case, the jet is coming towards us, so you can see the corkscrew shape of the kink. And the red is concentrated at the location where the Rayleigh-Taylor instability was happening. So there's something going on there. The EUV emission means the plasma's gotten a lot hotter there. We also see Whistler waves. We have a probe that's quite far from the whole configuration. The Rayleigh-Taylor was going on around here, and we saw a burst of Whistler waves at that time, which is something predicted by magnetic reconnection theories, and there is probably some magnetic reconnection going on at this point here. And this is a measurement of the magnetic field of the Whistler waves, and these are circularly polarized waves, and this circle pattern is the indication that this was really a circularly polarized wave. This is the magnetic field of the wave that as measured by the probe distant from that source. So now I want to say something about a model for what's going on. We're also seeing X-rays from this, and I'll say more about that. But I have this picture that in sort of the real world, you don't have a single jet. You've got magnetic field lines wrapped around each other, and it has somewhat of a fractal structure, and it's something like a rope, and each one of these strands here is carrying some of the current. And what's happening is that strands are breaking from time to time, just like in our experiment. And when that breaks, at least if I choke this thing down, I claim that that is equivalent to splicing a resistor into the electrical circuit. So there's this concept of an opening switch. Here's an inductor. There's inductance in our system, and there's a resistor, and there's a current, and there's a switch in parallel with the resistor. So that's an opening switch situation. So before this kinetic instability, we have ideal MHD. The plasma is a perfect conductor, so the switch is closed, and there's zero resistance here. But after the kinetic instability, the switch is opened, and so there's some resistance in there. This is like the traffic jam. You feel resistance on the freeway when there's a traffic jam, and that's going to do a lot of things. So it will produce a voltage drop that will, because the current of this is going to start decaying at the resistor, and there's an inductor here, so there'll be a voltage on this thing that goes like L di by dt, and that will appear across this resistor. It'll also be IR plus L di by dt has to be 0. So if this is a big resistor, you'll get an arbitrarily large voltage appearing here, and that will give you an electric field that can accelerate charged particles to large energy. Okay. So the kinetic instability comes about because the Rayleigh-Taylor instability chokes the jet cross-section. It impedes current flow. It causes a local potential drop. It's like a thumb on a garden hose. You have a garden hose, and you put your thumb on it. You get, it's like putting a resistor in there, and you get a big pressure drop, and the water goes out faster. So this turns out to cause a two-stream instability, which is a well-known plasma instability, but that's usually assumed to work only in a collisionless plasma, and we found that it actually will work in a highly collisional plasma where the collision frequency is much higher than all the other frequencies, higher than the growth rate, and it turns out that the collision's out and doesn't matter. And it gives a growth rate that's consistent with observations, and it's triggered basically by the electron velocity associated with the current getting to be bigger than the electron thermal velocity. So when I choke down this pencil, so that it could go faster than the thermal velocity of the particles in here, and that was what would set off this instability. So we've also done this in an experiment that simulates solar loops that's basically the same physics. And we also see a Rayleigh-Taylor instability triggering this. And the feature of this solar loop experiment is that we arranged it to be braided, so it's like this rope with strands. It's essentially something with two strands in it. And we saw a sequential breaking. First, we would see X-rays coming off that were 6 kilovolt X-rays, which is kind of surprising because this was a 2 electron volt plasma. We're seeing X-rays that were 3 orders of magnitude more energetic than the plasma temperature, but that's coming from that big electric field from the opening switch circuit. And this was happening twice, and we saw voltage spikes also that are associated with the voltage of the opening switch. Summarize, we didn't see any homogeneous turbulence. Instead, we saw spatially localized, dynamically changing structures, and we saw a sequence of MHD instabilities that led to the breakdown of MHD, because it was the Rayleigh-Taylor that was squeezing the thing so much that MHD didn't work anymore. And this squeezing caused the electron flow to be too fast for MHD. That's the opening switch argument. And that opening switch produced a huge electric field that would produce X-rays, Whistler waves, magnetic reconnection. And so we were able to see the coupling of MHD to physics beyond MHD. So just as an end note, I just published a paper that came out a couple of weeks ago going into the details of how the electric field could produce energetic electrons that would produce X-rays. Thank you very much.
Let's thank Paul for a great talk. Questions from the audience?
Yeah, thank you. So what are equations that describe physics beyond MHD? And was it deterministic or there is some stochastic?
No, it's not. It's a two-fluid equation with collisions included. So an equation is somewhat similar to the equations for ion acoustic waves, where there's a fluid equation for the electrons, a fluid equation for the ions, and they're coupled by Poisson's equation. And pardon? And there's collisions, lots and lots of collisions. But what's interesting is when you add the electron equation to the ion equation, the collisions cancel out because the momentum lost by the electrons from collisions is the momentum gained by the ions when you add those two. So it's kind of like MHD, but we're basically keeping the electron inertia in the convective term. There's an M U dot grad U term, where M is the electron mass that's discarded in MHD, and we're keeping that, and otherwise it's rather similar.
But in some local areas, they don't cancel each other, right?
Which?
They cancel each other in a larger area, in a box.
No, locally they're canceling.
They also cancel?
Yeah.
Other questions? Yes. You should use, go ahead. Go ahead.
Yeah, really nice talk, very nice results. Kind of two short questions. So one is, what about the ions? I don't know if you have any diagnostics that are measuring energetic ions, or is everything too fast to actually give ions significant acceleration?
No, the ions are moving. We see Doppler shifts of ion lines if we have ions. I mean, if we follow the ions, and the whole jet is moving at tens of kilometers per second, and that's basically the ion velocity, the center of mass velocity. The thing is the ion velocity, so the ions are important. We work with different ions. We work with hydrogen, argon, and we see the velocity of the whole thing is slower with heavy masses, heavy ions.
And can you describe the physics in terms of the electron approach? In other words,
well, that's for the kinetic instability.
Yeah.
In the basic jet, we don't. The electron mass isn't important. It's just straight MHD.
Yeah. Good. Thanks.
Other questions? Simon.
I'm sorry. Can you come? I'm a little bit confused about like the collision. So you say like it is collisional plasma or not?
Pardon? It's highly collisional. That's what's strange about this. This plasma is maybe 30 to 50 centimeters long and maybe a few centimeters in radius.
Yeah.
And as I said, it's dense and cold, so the mean free path is about a micron.
Okay.
And yet it's somehow managing to accelerate some electrons to 6 kilovolts without colliding. It seems highly collisional. It seems that electrons should get scattered in 1 micron and never get accelerated to anything, but there's some electrons that are getting accelerated so that they managed to get to 6 kilovolts. And this paper that I have here explains how that could happen.
Okay. And so in this case, when it's collisional, you mentioned at the beginning, like, oh, I can take like ideal MHD, but it will not work.
Well, it's ideal MHD, even if they're collisions, ideal MHD works if the resistivity from that collision can be ignored compared to everything else on the time scale that you're talking about.
Yeah. Okay. I'm sorry. Sorry. Another question. I think I've got maybe like a naive view, but about the kink instability. Like when you show the picture, it seems like it kind of swirl, like everything kind of swirl around like at the same times. And I was imagining like for like the kink instability going like a bit more like a stochastic like deformation, lateral deformation of like.
The kink's not stochastic.
No, but I mean like since it's like perturbation, it's like you expect to have like perturbation at different like position, but here like you show very like.
Well, to study the kink, you just assume you have a helical structure. You use cylindrical geometry, and you assume it goes like e to the ikz plus im theta, and you set m equal to 1, and you set k to some length, and you put that on your equations and see if you get a growth rate. And if you do, that means that a helical thing like that is growing.
Okay, so you really expect like these helical structures?
Yes.
Okay, maybe.
Okay, come on up. One last question here, and then we'll have some from the virtual audience.
Hi, thanks very much. I was just wondering whether you would comment on the wall of the device in the experiment, because as you pointed out at the start, J.B. Taylor's theory and even the definition of magnetic helicity requires having the magnetic field in a closed volume. So I don't know whether the wall is.
Yeah, so all this was happening basically before it knows about the wall.
Okay.
I mean, the device is very big, and so it only really has one boundary condition where those electrodes are, and the rest is like semi-infinite space. So yeah, we can get things that break off and form spheromac-like structures. That's what the original purpose of this was, but then we saw this other stuff that seemed more interesting, so we've been concentrating on that.
Did those spheromac-like structures do anything? Did they persist? Did they break up?
They would last a short time, and they did break off. We did this many years ago, but one of the things we would measure was the current in the broken off structure, and then we measure the current at our electrodes, the circuit going through the electrodes, and they were different. So that was telling you that the thing really was broken off. It wasn't carrying current coming back from the power supply. It was a little vortex of magnetic fields and currents sitting there, and it had helicity. And other people have studied that to death. So, but people hadn't studied this initial stuff very much.
Could you check whether those things were in Taylor states? Sorry to press the thing about the broken off spheromacs.
Well, yeah, I think they were. I mean, the Taylor state predicts a Bessel function, kind of radial dependence for the magnetic fields, and we saw that.
One more question here, if not. Okay, if not, does the virtual audience have any questions? Hearing none, let's thank Paul for a wonderful talk and thank everyone in this session.